Hello and welcome to this webinar on Deep Learning Made Easy with MATLAB. Deep neural networks are made up of many hidden computational layers. In a convolutional neural network, or CNN, some of these layers perform convolution. Most people tend to think that neural networks are black boxes which are extremely hard to fathom. I'm going to show in this webinar how you can look under the hood of a CNN and find out what is happening in the different layers so that you can gain insight into how we perform classification or find features using a neural net. Using MATLAB, it becomes simple to take apart a network and visualize the steps taken in each layer. Before we get started on activations, we need a bit of background into CNNs. A convolutional neural network is made up of many hidden layers which learn to detect different features. Filters are applied to an input image through convolution. The output of each convolved image is the input to the next layer. The other layers in the network add nonlinearity, these are ReLU layers, and downsample the data from layer to layer in pooling layers. The final layer is fully connected for classification, so in this case we can pull in an input image and correctly detect that it's a flower. So what do we mean by layer activations? In our convolutional neural network, we have these two-dimensional filters which we convolve with an input image using a sliding window. Different filters will emphasize different features in the output image. Lower level layers are going to show more simple features or shapes like colors or edges. Higher level layers are going to contain more sophisticated or complex shapes and features. This way, we can pull apart a neural network and try to understand what it has learned during training and the process it has followed. So what can you do with Neural Network Toolbox in MATLAB? You can design and train a convolutional neural network. You can predict responses or classify data using this trained network. You can also load pre-trained networks or perform transfer learning. Something else you can do is use the activations function to view layer activations for understanding different feature activations in different layers and channels. You can also use the same concept to create deep dream images, which we're going to look at later. In this demonstration, we want to find out if we can teach a convolutional neural network to learn about complex features like eyes in a face, even though it doesn't know what eyes look like and hasn't been trained to recognize them before. What we're going to start off with is loading in a trained network. In this case, we're going to use AlexNet. We're then going to read in a face image. We want to show activations of this AlexNet network for different layers in the convolutional neural net. We also want to investigate activations in different channels within those layers. So think of these channels as the filters that we're applying. We then want to find the strongest activation channels for eyes. So this image below is our end result. We want to find out which channels and which layers are going to activate strongly on eye features. So let's go into MATLAB and see how this is done. In this demo, we're going to visualize these activations of a convolutional neural network by looking inside different layers of the network. The first thing we're going to do is load in our pre-trained network like we mentioned. In this case, we're going to use AlexNet. Then we want to read in and show our input image. So in this case, it's going to be an image of a face. Now we want to take a look at what AlexNet looks like. So we want to see what our neural network architecture is built up as. So over here you can see that AlexNet is a series of convolution and ReLU layers with pooling layers built in as well. The last layers are fully connected. We want to show the activations of the first convolutional layer using this activations function. In this case, we're going to look at all of the different channels. So this is the generated image of all of our different activations for all of our different channels. This is a lot of images to look at all at once, and we want to see this in more detail. So we want to take a look at certain channels specifically so that we can gain some more insight into what's actually going on. In this first convolutional layer, we're going to look at channel 32. So a little bit of background here is we have different activations in our channel which are actually represented by pixels. And in this image, it's going to be a grayscale image, and white areas are going to show strong features, and darker areas are going to show features that don't show up so strongly. In this particular image, we can see that all of the red areas are much lighter, so this channel activates on red pixels. We can also find the strongest activation channel using some form of thresholding. So we want to try and find what the strongest activation channel is in this first convolutional layer. And this looks a lot like an edge detector. Now we want to take a look at a deeper layer. In this case, we're going to take a look at the convolutional layer number 5 and see what our images look like in this layer. You can see that this is starting to look a lot less face-like. Because there's too many images to investigate in detail again, we want to look at some more interesting ones. So let's take a look at the strongest channel once again. In this case, the maximum activation channel isn't actually as interesting for detailed features as some of the others. We can also see that in that image, the eyes are very dark. So let's take a look at some other channels. In channels 3 and 5, eyes appear very light, so we know that these channels strongly activate on eyes. We know that when we pass these images into the different input and output layers, we're going to get positive and negative activations and regions. When we pass these through a ReLU layer, we're getting rid of all of the negative parts. So when we take a look at the ReLU layer after convolutional layer number 5, it's more of just a black and white image. So this clearly pinpoints areas of the image that has strong facial features. So now that we've seen a couple of our channels which activate very strongly on eyes, we want to see if we put in another image, if eyes are still detected. Now there's a catch here. In our other image, one of the eyes in the face is actually closed. So let's take a look at how these channels activate when we feed in this different image. Over here you can see that these two channels still activate very strongly on eyes. So even though the network has never been taught to learn about eyes, it has learned that eyes are a useful feature for distinguishing between classes. In this way, we can use neural networks, and we don't have to use manual feature selection and detection in order to detect these more complex features. The next demonstration we're going to take a look at uses Deep Dreams. Deep Dream is a computer vision program created by Google. It uses CNN channel activations to detect structures and patterns in images. When the network is run in reverse, you can enhance activations in different layers with many iterations to create dreamlike image artworks. This is essentially making a network dream about objects in a scene. Something that looks a little bit like a dog in the scene, this activation is going to enhance that particular image in the scene in that section. This took the internet by storm, with people using the algorithm to create weird and wonderful images of morphed animals, like this dog and fish combo. Others have used these algorithms for style transfer to turn their regular selfie into an expressionist painting. In MATLAB, we have an execution of this open source algorithm with the Deep Dream Image function. You can select different layers and channels to activate, and then customize the function by altering the number of iterations you pass through and the starting image you use for the network. So for example, this is a simple image of clouds. If we want to see chickens in the clouds, for example, we can pass this through the Deep Dream Image function, and this is our output if we zoom in. So let's take a look at this demo in MATLAB. Once again, we're going to use AlexNet as our pre-trained network. First, what we want to do is take a look at the different layers of AlexNet once again. We know that in layer 23, it's a fully connected layer, and that AlexNet has 1,000 different classes. So we're going to use this final fully connected layer to dream about the different objects and creatures for classification. We're also going to select different channels within this. So these channels are actually the classes of images. So we're going to select 6 different classes in this case. These are the different class names that we've selected. So the first one is a hen, then a Yorkshire Terrier dog, a sheepdog, a fountain. We're going to use this Deep Dream Image function to generate an image. In this case, we're running the algorithm using a GPU. This is a CUDA-enabled NVIDIA GPU, so that we can train this a lot faster. Now we're going to show all of the images together. There was no input image for this, so these are all generated over white noise. So you can see these examples, for example, with the hen class and the theatre curtains. The Deep Dream has basically imagined these visualizations using the neural network. If we want to generate more detailed images, we can change some of the function options. So one thing we can do is increase the number of iterations. This is a more detailed image when we iterate more through the hen class. Another setting we can change is the number of pyramid levels. So this is actually dividing the image into smaller and smaller sections. We're going to use 5 pyramid levels in this case. We want to create a more detailed image that strongly activates the pot class. Once again, we're training this using a GPU. Here you can see that a very detailed image has been created of the pot class. You can see different pots containing many different flowers. Thank you for listening to this webinar. If you would like to know more, please speak to us about getting started about our different training courses and services. You can visit our website or contact us at sales@optimum.co.za to get a free trial of this software to test it out yourself.